Once again, thank you for being here. Thank you for being here. Yeah. So last week, not last week, Tuesday, we went through the lossless decomposition. Okay, there was this very complicated definition for that. But actually, there's only one. The easy way and the intuitive way to think about it is that after you have decomposed an original table into the smaller tables, is there a way that we can recreate my my original table or not? Okay, so that's the only thing. After I have split up my tables into smaller tables already, is there a way that I can recreate my original table? If there is, then it means that there is a lossless decomposition. The decomposition is not lossless. If I cannot recreate back my original table, then the decomposition is considered to be lossy. Okay, so that was the main thing. So I went through the first example. I think maybe I just go through this one first. So we went through this example whereby we first have the original table. We say we split into table R1 and table R2, and these are the empties. And we create a table. So I have on my X, I will have all the attributes A, B, C, D, E, and then I have R1 and R2. And for R1, I have B, C, D, and I will put a distinguished variable there. On R2, I have A, C, E, so I'll put the distinguished variable there as well. So the next thing that we want to do is, I want to check to see whether am I able to create, to use algorithm to have one entire row that is full of distinguished variables. And in that case, right, what we do is that we will go through my functional dependency one by one. Okay, so let's try to do that now. So let's look at AB implies C. AB implies C. We have on my left hand side is AB. So the rule is the following. On the left hand side, I must find two or more rows that has the distinguished variable. So AB implies C. I do not have two or more rows on my left hand side that has the distinguished variable. So I only have one here and one here. So I don't have. So I don't have to consider this functional dependency for now. C implies E. Okay, so in C implies E, I realize that, oh, I have two distinguished variables on my left hand side. And E, there is one distinguished variable here. And so, so my second condition is that on my right hand side, I must find at least one row from my first condition that has the distinguished variable. And it also passes the third condition, whereby there's at least one row from my first condition with a non-distinguished variable. And so I can add a alpha distinguished variable here. So then we will then go on to the next functional dependency of B implies D. Because B implies D, there's nothing we can do over here, because on my left, there's only one distinguished variable, and so there's nothing we can do. And we come to E implies A, and now we realize that on E, we have two distinguished variables there, and so it satisfies my condition 1. A has only one row with a distinguished variable for my first condition, and so it satisfies my condition 2. It also satisfies my condition 3, and so I'll add a distinguished variable here as well. And at this point, I realize that for my row R1, I have an entire row of distinguished variables, and so this is a lossless decomposition. So that was what we went through last week. Sorry, on Tuesday. So the thing that I maybe want you all to not want you all to understand that maybe to just to highlight is that the way the FDs are given here is very nice, but it may not be so every time. So what I mean by that is that let's imagine if my FDs are given like E implies A, and then A, B implies C, and then C implies E, B implies D. So if we were to have, let's say if the question gave us the FDs in this manner, and I do the functional, or rather I try to carry out my algorithm using this first, I'll find that I'm unable to fire this condition 1 and this condition 2. I don't need to consider this. This is also wrong. I will be able to fire this because over here I have 2 alphas here. I can put alpha here. And let's see if I just go down and B implies C, then this is also wrong. So it is incorrect for me to stop now because I have added an alpha, or rather I added a distinguished variable which will affect one of the left-hand side of my functional dependency. So by right, I should go back again to my functional dependency to check to see whether will any new functional dependency be able to be used or not. Yeah, so that is one point I wanted to highlight to the class. Okay, and then okay, so this is something that we talked about already. Okay, I'll just go through one more. Yes, is n square. In fact, if you want to be strict, maybe it's nm, where m is the number of FDs. So yeah, so mn. Yeah, I think mn will be mn. Yes, quite sad. Let me see. Depends. Is mn the best that we can do? It may not be the best that you can do, you know. Let me see. Yeah. I think we have to go through MN. Even if I use a hash table, may not work as well. Yeah, I think the best may still be MN. There may be a way, there may be a trick for us to do it, but let me think about it. My attendance. Thank you, Ryan. Okay, so so quickly I'll just go through this example. We have R1, R2. So I went through this example last week already, but now I'm going through the entire thing because this is also what you'll be expected to do. So C, S, J, D, P, Q, V, alpha, 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 like that. So funny. Hey, sorry. Yeah. So wait, I saw long. So don't make the same mistake as what I did. So we look at the table. So table R2 is SDP. Table R1 is C S J D Q B. C S J D Q B S D P. Yeah. So this is how we want to be able to draw the 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 table. Okay. Then we'll go through the FDs one by one. Let's look at the first FD. I don't have C on my left hand side, so this one is fail. J P. I don't have the distinguished variables also on both, so this one is also fail. And SD implies P. SD implies P. So left hand side it passes. Okay, SD it passes my left hand side. Right hand side P it also passes my right hand side. And so I'll be able to add a distinguished variable here. And so this decomposition is then lossless. Okay, so that is the second example. But we did go through these two examples last week, so that's why I'm going a little bit faster. Or rather Tuesday. Okay, so yeah, so we went all the way to. Oh no, we went all the way to this. Yes, we went all the way to this example, and that was where we stopped. Okay, because I think I mentioned that this example is quite long. Okay, let's go through this example. So right now we have this table A, B, C, D, E, F, and I have these functional dependency. And we are going to split the table into 4 tables. So A, B, C, D, E, F. R1 is AB, R2, B, C, R3, A, B, D, E, R4, E, F. Okay. So these are the so-called 4 tables that we have. The first thing that we want to do is let's go through the FDs one by one. So A, D, on my left hand side, don't have the distinguished variable is not there. So we can't do anything here for now. Let's look at the second one where we have the B. Oh, you see, B has so many of distinguished variables here. And we can see that it also passes condition 2. Good. And so we can add alpha 1, alpha 1 here. Okay. Next, let's look at this example. E implies F. E implies F. Okay, we have 2 alphas here. We have 1 alpha here. So we can add 1 alpha here as well. Okay. Very good. So as what Brian pointed out earlier, this is an NM algorithm. So we may need to go back to cycle through the FDs again. And so we now have AD implies E, A, D. And now we find the E. There are distinguished variables here and here. And there is at least one on my right hand side. There's a non-distinguished, there's a distinguished variable. And there's at least one on my right hand side. There's a non-distinguished variable. And so I can add the alpha here as well. All can follow. So this is using this, I can now create back add a distinguished variable here. Okay, are we done? So apparently not yet. Not yet. So after this has been done, we now look back at B imply D, nothing has changed, but E imply F, we now find that E is here, and we are able to add another F, there's a non-distinguished variable here, add a F over here. Okay. Unfortunately, I think we are done over here. There's nothing else we can do. Is there anything else that we can do here? Yeah, it doesn't seem to be. And so this example seems to be a lossy decomposition. I cannot get any row with all the alphas. Okay, so this is just what I did earlier, which is I used the this to fill up. Did I do that? Yes. Yeah, I use B to fill up these two. After that, I use E to implies F to fill this one up. And after that, I use AD imply E to fill up this one. And then after that, last one. And we find that this is actually a lossy decomposition. Okay, very good. Okay. So, okay. So earlier we talked about lossy decomposition. Now the second thing is dependency preserving. Actually, two different things. So the first one is, can we create back the table or not? The second one is we want to check to see if do we have all the functional dependencies preserved or not, even though we split up the table into two or more separate tables. Okay. This one is okay, is quite, it's not complicated, but it's very tedious. It's just a very, very tedious process. And we'll go through it. So for example, I have the table A, B, C, D, E. And then I have the following functional dependency over here. And suppose I split up into these two tables. If I want to see if any of the functional dependent, or if the functional dependencies are preserved or not, unfortunately, we need to analyze them one by one. So this is a very sad and long process. So it is similar to doing joins also across different tables. We'll do it now. Okay. So let's look at the first FD and we see if is this FD preserved or not. Okay. Notice I have these very, very, very long steps. So basically, the algorithm is like that. First, we define a variable known as Z. For the FD that we want to assign, or want to check, we will assign the left-hand side of the FD to Z. So in this case, the left-hand side of the FD is equals to AB. And so we will assign AB to be the value of Z. So this is the first step. After that, we will intersect Z with R1, which is B, C, D. So essentially what we are trying to say is that I want to see from the left side of my functional dependency, are any of the any of the attributes there in my table or not? So that's what we are trying to say. In this situation, we realize that the intersection will give you B. So Z is AB, R1 is BCD, the intersection will give you B. And the next step is I want to find the closure of B. The closure of B based on this functional dependency is equals to BD. You all can know why I get this, right? Because from all my FDs, I know that my closure of B is equals to B because B implies D, and there's nothing else I can do over here. So this step is just saying for my left side of my FD that is in my R1, what is the closure of it? The next step is I will intersect the closure with R1, and this will give me BD. What this tells me is that my closure of any part of my left hand side is also I want to get the parts of the closure in my left hand side that is also in my relationship R1. Okay, and finally a union. Sorry, I did wrong. Union it with Z. So BD union Z will give me A, B, D. Okay. Okay. This is just the first part. Yeah. Okay. The next step is that I have to repeat all this for the other table. Yeah. So very tiring. Yeah. So I got to repeat all this for the other table. But now my Z is equals to A, B, D. That's my mouse off. Now my Z is equals to A, B, D. And I have to repeat this entire step for R2. Okay, so let's do this together. So now I know that my Z is equals to A, B, D. R2 is A, C, E. The first thing is I intersect between Z and R2, and the intersection is equals to A. So not so far, yeah. So the next thing is I find the closure of A, which is equals to A again, which is same as this step, and then intersect with back to my table, which is equals to A, and I union it back to my Z, which is A, B, D. Okay. At this point, we can stop because at this point, I don't need to check this Z again back with my R1 because this is exactly the same as what we got after I completed this step, and that is why I can stop at this step. I can stop at this step, and I can then declare that Z does not contain the right hand side. which is the value of C. And so this FD is not served. Okay. 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 Okay, let's do this. Let's do the next one. C imply E. Let's do C imply E. Okay. This is B imply B. I don't know why I didn't do C imply E, but I think let's do it together. Let me erase this one first. So we follow through all the entire steps that we did. First, we assign Z to the left-hand side, which is C. I think I know for why, because very fast. Z is equals to C. I intersect Z with R1, I get C. C closure equals to C E. So from now we see I'm actually not doing anything special. So I'm just doing what is there. And C closure is equal to CE equals to A C E. Is that all? I think that's all. I think that's all. And then now I will intersect A C E, intersect with my R1, and this is going to give me C only. Yeah, nothing else already. Yeah, this nothing else already. So this gives me back to C, and I union it with Z, and Z is still equals to C. Okay. So this is for the R1. We cannot stop here yet. So you have to check with R2. So R2 first is intersect with Z intersect with R2, and so Z intersect with R2 will give me back C. I find the closure of C, which is going to give me C A C E once again. I intersect back this with R2, and I'll get A intersect R2 equals to A C E. I union this, A union Z will be A C E, and so I can conclude that C imply E is preserved because the right hand side E is in my Z. Is this part clear? Do you need me to go through this again? Yeah, it actually it can be a bit confusing, which is why we stress so much on finding the functional dependency so much earlier in the last 1 or 2 lectures. Because if you can catch the functional dependency well, right, then this portion is easier for you to understand. And the closure and everything, yeah. This part will be easier for you to understand. Anybody need me to go through this again? Okay. If everybody is very clear on this, then why not you try this one? Maybe you think about okay. So dependency preserving weightage yeah, quite high, I think. Because second half only left this guy. I mean, I'm not testing you on the second half, what? So if I don't test this, then nothing to test already. So yeah, yeah. So yeah, because all this is second half, ma. So I really spent 2 weeks on this. So 2 weeks out of 6, so at least one third lah. And maybe even yeah, and next week the quiz is all on this. So you try the B imply D first. Thank you. Maybe give you until like 9:04. No, fast. Wow, Jia Wei very fast. Yeah, it's preserved. Very good. So Mr. Jia Wei solved the problem. So first we set Z to be equals to B or Z equals to B. We intersect Z with R1. So Z intersect with R1 is equals to B. We find the closure of B, which is equals to BD. And then after which we will intersect this back with R1, which is equals to BD. And after our union, BD, it should give me also BD. And at this point, I can conclude that the right hand side is part of my FD here. And so, yes, very good, Tawi. And so the FD is preserved. Okay, so notice when I did C imply E, I got to do all the complicated steps. Left, right, left, right, left, right, right. When I did B imply D, right, actually I can do half of it and I can stop. So do you notice something very unique about B imply D? I can actually do a short circuit of B imply D. And meaning that actually I can even don't do all this and I know that that is preserved. Yes, very good. Both elements B and D are on the same table. So if I want to be very fast, right, or well, not say very fast, but by right, I can look at this, right, and I can say, oh, this one preserve, confirm. Because B and D are in the same table. I can, it's the same thing, I can also look at this, EA, this one confirm, preserve. Because E and A are in the same table. Okay, so that is the very quick way of looking at it. If they are in the same table, I can definitely say that they are preserved. If they are not in the same table, it means that I don't know, and I will have to go through the complicated step that I've shown you earlier. Okay. 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 Let's go to the next one. So this is what I said. I did earlier. So B implied D, that is actually exactly what Zhao was doing. So then the Z contains the right hand side D, and so it is preserved. And I was saying earlier, B implied D over here is in my R1, and so definitely I'm sure this is being preserved. And the last one, E imply A. So actually, if you look at this type, right, is empty set. Sorry, is empty set, right? Then you go here to intersect with empty set, and then when I find the closure, when I find the union, and I intersect back, I will find that my right hand side is also in my Z, and I can then declare that it is preserved. But the short circuit is that both left hand side and right hand side, they fall in one table. So and in this right hand side, left hand side, they're not in this table. So because of that, I can say, oh, this FD is not preserved. Oh, sorry, this FD is preserved because it is in my second table. Okay, let's look at this example. Let's find if the FDs are preserved or not. So if we look at this, we can immediately see that there's a few shortcuts that we can do. So this one, very quickly, is this preserved? We should be able to see immediately that this is preserved because of R3. R3 has A, D, E, and so we are sure that this is definitely preserved. Let's look at the second table, which is B, D. In the same way, we can also say that this is definitely preserved because I have B and I have D on the same table. And so this is also definitely preserved. EF, do you think this is preserved? EF is also preserved because EF is over here, and so we are sure that this is also preserved. So once both the left hand side and the right hand side are in the so-called the sub schema, we are 100% sure that they are preserved. Okay, so this is what I see here. So if I split into these two is the same. How come I repeat? Accidentally repeat. Sorry. Yeah. So if all the left hand side and the right hand side are in the left hand side and the right hand side of the FD are in the sub schema, then the FD is preserved. However, if they are not, then we can neither declare that they are preserved or not. So we have to use just now the long way of doing it. So in this example, as I said earlier, this is preserved because of R3, this is preserved because of R3, this is preserved because of R4. Okay. Let's look at this next slide. Okay, so I tell you what, maybe the time is also 9:10 already. Let's do a 10 minutes break. And during the break, right, you all try to do this question. Then when I come back, then we will go through this question. Then we just use the break to also try out this question. Thank you. I will talk to you in 10 minutes time at 9:20. Sorry. See you later. Okay, welcome back. So okay, let's do this together. So let's say I have this table and I'm splitting it into two different tables or sub schemas here. So I want to check if my functional dependencies are preserved or not. So remember previously we went into look into the lossy decomposition. Now we are looking into the functional dependency. Okay, so first thing, SD implies P. So first we know that this is in R2, and so this is preserved. And now this is fine. Now we have these two other subschemas. Okay, this SJDPQB, SJD, oh no P. So this is not found in any of the relationship. So we don't know. We cannot conclude if it is preserved or it is not preserved. Same thing for this. J, P implies C. Same thing, this entire three attributes, they are also not in any of the sub-schemas. So in the same light, we cannot conclude if they are preserved or not preserved. So we have to check. We have to use the very long way to check. So let's do this together. So I hope you all managed to get to this point just now. The next few parts is the algorithm. So step 1, we take the left-hand side. Oh, sorry, we will look into this FD first. Step 1, we take the left-hand side and we assign it to Z. Step 2, we intersect it with R1, and this we get equals to C. Step 3, we find the closure, which is CSJDPQV. CSJDP, yeah, this is the primary key, yeah. So everything. So step 4, I actually union, or sorry, I have to intersect this with the R1 to give me CSJDQV. And step 5, sorry. I will intersect, union this back with CSJDQV, and this will give me CSJQV. So this is the first one for R1. Next, R2. We have to repeat this entire thing for R2. So first, I have to intersect this with R2. So R2 is SD and P. So I will have so Z is CSJDQV intersect with SDP intersect with S, maybe like that, clearer. So this will give me S and D. Then the next step is I find the closure of S and D. S and D closure equals to SDP because of this. And then I intersect SDP with R2, and this will give me SDP. And I Z union with SDP, and this will give me CSJDQV intersect with union with SDP, and this will give me CSJ D P Q V. And so at this point, we can conclude that the right hand side contains the functional dependency, and so this is preserved. Okay. Hope you all got to here. Any questions with this functional dependency? You can you all follow what I'm doing? Do you all need me to repeat? Anybody need me to repeat this one? Sure. Then we will go to the JP implies C. If there's a better way to erase this, let me know. Is there a better way to erase this? Don't have. Is there a clear slide or something? Don't have. Oh, yes. Yes, very good. So, okay. So let's do this. JP implies C. So this is the second thing we need to do. So JP implies C is not found anywhere. So we need to do the steps one by one. So step one, I need to assign Z to my left hand side. JP. And then step two, I need to Z intersect with my first table, R1, and this is going to give me C. Wait, sorry, C. This is going to give me J. This is going to give me J. Is that all? There's no P. There's no P. Next step, I need to find the J closure. It's going to be just J alone. And after that, I will intersect back with my R1. And this will give me J. And I will union back with Z. And this again gives me J only. Okay. So at this point of time, we still don't know anything. Yeah, so we still not. This is yeah, correct. Yeah, so we still don't know. Sorry, I thought I saw a P here, R1. Yeah, so we still don't know. So we have to go to my R2, step 6. So I will have to do my Z intersect with my R2. This is going to give me an empty set because J is not there. And so we don't need to do the rest. We know that Z at the end of this will still be equals to J. And so we can hence conclude that JP implies C is not preserved. So you notice that in here, we are able to recall actually this example is actually the same example as what we did earlier, whereby we can do a lossless decomposition. Let me see. I remember here is one of this. Remember, yeah, this example. So it's actually this example here, where we actually can make this to be a lossless decomposition. But then we cannot get back my functional dependency. Let me see. Did I screw up somewhere? Where's okay here? Oh, there's a question. Z union J. Z union J. At this point of time, Z is just J. Also, no, Z is JP. Sorry. Yes. Sorry. Yeah, I screwed up here. So Z is JP. Z is JP. I screwed up. Sorry. So this is JP. Hey, thank you, Hong Wei. Let me see. Did I screw up anymore? Yeah. Z union J. Yeah. So Z is JP. Sorry, I screwed up here. So I screwed up here. So this is JP. So I should redo this one. So Z union. Sorry about it. Let me do this again. Yeah. So Z now thank you Hong Wei for pointing out that Z is JP. JP union with R2 is equals to P. And now I need to find the, I never screw up, right? Seems to be fine. I need to find the union of P. Union of P is equals to P. And then I need to do the intersect with my R2, which is also equals to P. And then now lastly, Z equals to Z union with P, which gives me back JP again. Okay, let me check if I screw up or not. Yes, this is correct. Okay, so this is correct. Okay, so sorry. Okay, so this is correct. So we notice that in this scenario, my JP implies C is not preserved. Okay. So notice in this, right, we have 3 FDs. In this 3 FD, this is preserved, this is preserved, this is not preserved. So in this decomposition, I have FD2 not preserved, but this is a lossless decomposition. Okay, it's lossless. Why I can know that it's lossless decomposition is because this is the same example as what we did here. I hope this is the same example. Yeah, I think this is the same example as what we did here. So in this example, we found that we are able to recreate back my entire table from my sub schemas. But although I have recreated back my entire table, but one of my FD is lost. Okay? So with this, we actually can find that there are cases whereby we call it like a lossless decomposition, but we lose a functional dependency because of us decomposing the tables in a certain manner. Okay, let's look at the solution. So this is for the first FD. So for first FD, I assign Z to C. After that, intersect it with R1, and I will get C only. I find the closure of C. The closure of C based on this will be CSJDP QV. I intersect it with R1 to get this. I'm sorry for my sign. And then finally, I union it back with my Z. So CSJD QV. Okay, so this is the first part, and then I'll try with the second part. So I take the Z, which is CSJDQV, intersect with R2. R2 is SDP, and this it will give me CSJDQV. This will give me SD. I find the closure of SD, which will give me SD and P. I intersect SD and P back with R2. This will give me SD and P again. I union it back with Z, will give me CSJD, QV, and now I have additional P because of this. I see that my Z contains my right hand side of SJDPQV, and so my FD is preserved. So we went through this earlier. The other part was where I scroll a little bit. So I first assign Z to JP. I intersect Z with R1. So R1 is this. Z is JP. Only J comes out. Find the closure of J. Closure of J is still J. Intersect it back with R1, I still get back J. I union J union Z, I get back JP. After that, I would repeat it for R2. I intersect Z with R2. Z is now JP. This will give me P. I find the closure of P, which is P. Intersect it back with R2. R2 is SDP. I still get back P. I union it with, I don't know why my sign is also back. Union it back with, my pen is not working. Union it back with Z. I get back JP. I don't, does not, Z does not contain right hand side C, and so FD is not preserved. Okay. Does anyone need me to go through this? Because we are going to move on already. Tell you what, maybe we go through some example to reinforce. Okay, maybe you all need more example. Let's do this. So instead of going on with the normal form, let's go through some example. Oh, yeah, this one. Oh, yeah, this one need normal form. Cannot. I need the normal form. Okay, sorry. Yeah, I think we need to. I cannot do the example now. We need to go through the next one. So sorry. Yeah, sorry. You need to go through this. Anyway. Oh, do you need me to explain this example again, or everybody is comfortable? Okay, if all is comfortable, I will go on to the next part, which is the normal form. Okay, so the normal form is how there are certain rules, right? How we define the table decomposition. I have briefly mentioned this in the first half of the course, but I mentioned it very briefly and also in passing only, because not yet the focus. So right now we are going to focus on what is the best way to decompose certain tables. So first thing is, of course, we want to avoid too much decomposition. So there are, you see two tables here. What is strange about these two tables? The strange thing about these two tables is that actually, let's say this is flight number, defines DO, departure time origin. Flight number also defines AD, um, maybe destination, let's call this N. So probably F defines DO, probably F also defines A and N. So in this case, then it's a lot easier to do this, right? Yeah, it probably is a lot easier to just have one big table that has a flight number and departure, origin, arrival, and destination. Easier for you to have that. So this is a too much decomposition kind of a scenario, something that we want to avoid. Okay. So the schema enables us to identify a good schema. So of course, what is good? Good is a very rough, very subjective measure. So because it is subjective to people, so we have not we lah, but the a few measures of this good has been defined. So they are called the first normal form, second normal form, third normal form, and the boys called normal form. And there's also fourth and fifth normal form. Then to be frank, we usually go up to at most B, C, and F, which is the boys called normal form. And actually, to share with you, even for me, I typically stop at the third normal form. The BCNF is really not required. So it's maybe it's good to have, but typically if you start at 3NF, it is often good enough. So the question then now may be like, what do you mean by 3NF or BCNF? Yeah, so we will explore that now. Okay. So firstly, we have some definition. We have talk about attribute. There are two types of attribute. We call them the prime attribute and then the non-prime attribute. Prime attributes are attributes that are part of the primary key, and non-prime attributes are attributes that are not part of the primary key. Okay, so we call maybe I shouldn't use primary key. Maybe I should say candidate key. I think CK will be better. Yeah. So we had this. Assume we have this relation and this FD side, and we have found that the primary key of this table is equals to CEFADB. So in this case, and assume that this is the only key candidate key we can find, the prime attributes will then be C and E because they are part of my candidate key. And the non-prime attributes are FADB. These are all the non-prime attributes. So that's just a simple definition between prime and non-prime. Okay. The first normal form is the following. And Okay, the domain is atomic if elements of the domain are considered to be indivisible units. Um, okay, so in this scenario, right? In this scenario, do you think is uh, this is uh, this is this is first normal form? This one got some issues, right? You see, you can tell that there are some issues here. For example, this is not not this will fail the 1NF. Okay? You cannot have rows that like combine rows in the 1NF. So this by itself is already not a database 1NF form already. Okay, so firstly, the rows must be single rows. Somehow I forgot what's the right term to describe rows. Yeah, but it must be a single row for every. The rows must be distinct for every single row. For every single row, it must be distinct. Yeah, so that's the very first thing. The second thing is that the address over here, this is also not atomic. Okay, so if I have so-called a combined so-called attributes within one attribute, then that will not be considered a 1NF. So if we are very strict about this, we would say that this, because of this rule, is also not the 1NF. If you are really very strict about this. Okay, of course, sometimes as we explored earlier, due to whatever things that we may consider these to be 1NF, but by right, if you are very strict, we would even say that this is not a 1NF kind of database already. Okay, so yeah, so these are the various things that will make a 1NF function. The rest, right, are typically the case. Okay, the column must have a unique name, right? This is again a rule of relational databases. We are in week 9 now. Possibly in week 11 or maybe 12, 13, or maybe 12, maybe 12 around there, we'll explore non-relational databases like MongoDB. And we will find that when we have non-relational databases, right, your columns can be anything. Yeah, so for this table, for this record, I can have this kind of table column name. But for another record, I can have a totally different column name, and it's fine. Yeah. So that is a phenomena that we see in non-relational databases. However, for here in 1NF or in relational databases, right, my columns must always all be the same. So in this scenario, we see that this part is not a 1NF. This part is also not a 1NF kind of thing. Let's look at